In this section, we're going to get a preview of calculus, and with that, we're building to the idea of instantaneous rate of change. So the idea of how is a function changing at a single moment. But before we can get to kind of that microscopic level of analyzing how the graph is changing, we're going to start by talking about average rate of change, which is over a larger interval. How does our function change from x equals a to x equals b? And with that, what we'll do is use f of b minus f of a over b minus a. Now that structure there should look somewhat familiar to you, and it should look like the slope, because it is. With that, we have a difference in output over difference in input, which directly links to slope between 2 points. So really with these, we're finding slope, but we're going to call it average rate of change here. Where it differs a little bit, and we'll talk about this in a video regarding secant lines, but the idea is that our function could be doing all sorts of things, meaning it doesn't have to be linear. But what we can do is imagine what if it was linear between two coordinates anywhere on our function. And if I want to know what's happening on average between those 2 points, I connect them with a straight line. And my average rate of change is going to be equal to the slope of that line. That line that I'm graphing there is called the secant line. So that slope of the secant line is going to tie to our average rate of change. And with that, we can get an idea of overall how our graph changed between those 2 points without all the extra curves in there. So let's say we have a function 4x squared minus 3, and we want to find the average rate of change from x equals -2 to x equals 3. So what we're going to do is to find the average rate of change. We'll take h of 3 minus h of -2 all over 3 minus -2. And what I'll do is I like to do this kind of work on the side of plugging in 3 into the function. So we're going to have 4 times 3 squared minus 3, which will be a 4 times 9, so 36 minus 3. So we're getting a 33 out. And then h of -2, we're getting 4 times -2 squared minus 3, so 16 minus 3, so 13. And then what we could do is make a nice little substitution so that 33 is equal to h of 3. So we're going to replace our function notation there. And then h of -2 is equal to 13. Replace our function notation there. So we'll have 33 minus 13 in the numerator. And in the denominator, that 3 minus the -2, or 3 plus 2. So we're getting a 20 over 5, which is 4. So what that tells me is so this is a quadratic function, so we have curvature to it, but if I draw a straight line from where x equals -2 to x equals +3, there's this rate of change of 4. So I can tell it's increasing between those 2 points and at a rate of 4. Okay, let's go to this word problem, and we're going to see this word problem throughout a few videos here, where we'll kind of get this idea of average rate of change and slowly morph it into this idea of instantaneous rate of change. So what we have here is a population of bees, and they start at their peak population July 1st, 2011. And then from there, we're going to measure their population. Unfortunately, it's decreasing, but in T months after July 1st. So B is going to measure the number of bees in thousands, and then T is going to be our amount of time that's passed. And the function we're focusing on here is this 32 minus 2t squared. So it's not a constant rate. We have something quadratic here, so it has a kind of changing rate of change, if you will. But we can still talk about this average rate of change between 2 points. So from the time they hit their peak, which was occurring when t equals 0, to when they had officially died off, so what we need there is we need to know where is the population equal to 0. So let's go ahead and solve that off to the side here. So if I needed to find where our function is equal to 0, so I'm going to go 0 equals 32 minus 2t squared, and then we're going to solve. So 2t squared is equal to 32, t squared is equal to 16. square root of both sides, and we'd have t equals plus or minus 4. However, in the context of this, it would only make sense to have the positive. So when t equals 4, that's when our population dies off. So with that, I'm going to look at the average rate of change from t equals 0 to t equals 4. So we're going to go b of 4 minus b of 0 over 4 minus 0. B of 4, we actually already know from how we set it up, that should be when the population is equal to 0. Minus, if we plug in t equals 0 to get that maximum population, that would be a 32 over 4 minus 0. So we're getting a negative 8 out. So what that tells me is that when we're looking from t equals 0 to t equals 4, which, if it helps to write out what that represents in terms of the months, we have July, August, September, October, November. So what we could say is between July and November, we could even say July 1, 2011 and November 1st, 2011. The population decreased by 8,000 bees per month, because that's our rate of change. And we just want to throw in on average, because it wasn't a constant change. It wasn't always that for each month, but on average, that's what we saw happen. Okay, so now let's say we just want to get a general form of given any two times, so we're going to call it t0 and t1, what is happening with this rate of change? And we want to simplify that. So what we're doing here is looking at, what if I take b of t1 minus b of t0 over t1 minus t0. And what I'm going to do is go ahead and substitute into our function for b. So that was 32 minus 2 times t, but now we're inputting t1, and then that's squared. And then we're going to be subtracting, and parentheses are super important here because that negative needs to distribute in. So 32 minus 2 times t0 squared all over t1 minus t0. So simplifying that down, we're going to end up with a 32 minus 32. So those are just going to cancel out with each other. Then here we're going to have the minus a negative. So it's going to be a negative 2t1 squared plus 2t0 squared all over t1 minus t0. And we're going to keep simplifying. And something that I want to do here is sometimes we reorder it so that the positive is first. However, what I want to do right now is keep these input values matched up with each other. So instead what I'm going to do is I'm going to factor out a negative 2 in the numerator. So negative 2 coming out of there. So I have t1 squared minus t0 squared. And I have a nice difference of squares there. So a little factoring, which gives us a nice cancellation, all to just reduce this down so that we can use this instead of plugging into the full formula. So I'm going to end up with a negative 2 times t1 plus t0. So that right there is a simplified form of our average rate of change given t0 and t1 for our function b of t. So what this function does, or what this average rate of change formula is doing, is that we're given 2 times here. So it's like given 2 separate times and calculating. Another way that we could calculate this average rate of change is using something called the difference quotient. And with the difference quotient, it changes a little bit in that it isn't 2 separate times. So with average rate of change, we were using t0 to t1. What we do with the difference quotient is we think of the interval from x to x plus h, meaning we have some time that we choose, and then we're going to look at that time and add on a little bit to it. And that value could change. It could be adding an entire month, it could be adding 2 months, it could be adding a little moment in time, a second or something. What we can do is this is how we'll get to this idea of instantaneous rate of change of as we shrink this interval that we're looking at for our average rate of change. Now, this function right here, this is tying to our average rate of change because we have our f of x plus h minus f of x. And then just imagine if we had in the denominator that first input x plus h minus h. Nope, I need to rewrite that. In our denominator, we would have had x plus h minus x. And with that, that leads to just a denominator of h. There we go. So this right here is our difference quotient, and just changes it into, instead of two separated time intervals that we have one single time plus a little bit. So what we're going to do here is like we did up above in part B, we're going to look at the difference quotient, and that is missing our 2 right there. 32 minus 2t squared with our difference quotient. So let's take a look at what that looks like. So we are going to do b of x plus h minus b of x all over h. All right, this is some good algebra review as well as our function notation. So we are going to have 32 minus 2 times, and then we'll have an x plus h squared. You know, I am going to change instead of x, sorry, it's just a notation thing. It isn't going to change the math at all, but just for consistency, let's use t there. Okay, and then we're going to subtract our function in parentheses of 32 minus 2t squared all over h. Now this difference quotient is going to be something that comes up quite a bit in calculus, especially at the beginning of the course. So want to get used to kind of plugging into this and simplifying. Okay, so I have 32 minus 2 times, and then I need to expand out that t plus h squared, which would be a t squared plus 2th plus h squared. And then I'm going to distribute that negative for a minus 32 plus 2t squared all over h. And let's see, 32 minus 32, so those are going to turn into a 0. I need to distribute that negative 2 in, so negative 2t squared minus 4th minus 2h squared, and then at the very end that plus 2t squared all over h. Negative 2t squared plus 2t squared, that's going to turn into 0, and then I can do a nice division of h from each of these terms. So I'm ending up with negative 4 times t minus 2h. So we end up with these two simplified forms. One of these is our average rate of change, and this one right here uses our difference quotient. And when we're plugging in, it's just the difference of kind of how we set up our intervals. Okay. So from there, let's start taking a look at what happens. Oh, I've kind of talked about this already. Yeah, let's just see though that if we plug into this, so finding average rate of change, so we take our function value at the t plus h minus the function value at that first input over t plus h minus t. We get a nice cancellation, and it turns into our difference quotient. But the main difference is being how we're setting up our interval. Are we thinking of it as a starting point and then moving from that starting point? Or are we thinking of it as a beginning point and an ending point? Okay, Use the formulas found for the average rate of change and difference quotients to determine the average rate of change over the intervals 1, 3, and 3.5. So, for 1, 3, what I'm seeing is that, and actually, we could use either, no matter what. We could think of this as 1 and 3. We could also think of this as 1 and 1 plus 2. In fact, why not? Let's do both, so we can see that the formulas give us the same thing. So for 1 to 3, I would be using that average rate of change, which tells me to take -2 times, and then add those two values together. So that would be a -2 times 4. There's our -8. If I thought of it as 1 to 1 plus 2, then what I could do is use that -4t minus 2h. So using that difference quotient, we would plug it in as -4, and then we would have t is 1, minus 2 times h, which our h would be that plus 2, which would be a -4 minus 4, which is also -8. So it's measuring the same thing, just with these two different notations. Then we could do the same thing for 3 to 3.5. If we treat them as two separated values, we can use that average rate of change. If I want to think of it as these kind of differences of starting point and then moving from that starting point, so a 3 plus 3.5, then I could use that difference quotient. So average rate of change told me to take -2 times the addition of those two pieces. So let's see, a -2 times 6.5, so -13. And then the difference quotient was a -4 times our starting value, minus 2 times our increment, which was a positive 0.5. So we have a -12 minus 1, which is a -13. So two different ways to measure the same thing. But what we can notice is that with the difference quotient, and we're going to start thinking about how do we make these intervals smaller, and we can do that just by shrinking h right here. So what you can do is kind of make a starting point, and then from there make this difference value smaller and smaller and smaller so that we're getting close to 3, and we want to get infinitely close to 3. So let's think of this idea of what rate of change is occurring exactly when t equals 3. We're going to see how this compares in terms of average rate of change versus the difference quotient. And, major spoilers here, but we've already kind of seen it. They're going to be the same. We're going to get the same average rate of change. So how these tables are set up is so that right here in the middle, it's a different pen, right here is where 3 is occurring. We just can't calculate the average rate of change from 3 to 3 because it's at the same coordinate. It's going to give us nothing. In fact, it's going to be undefined. So with that, we can't see what's happening at exactly 3. So that's where we need to get as close as we can to 3. So that's what we're doing with this table. So average rate of change, we're looking from 3 to 2, to 2.5, to 2.75. So what we're doing with T1 is we're getting closer and closer to 3. So if we're finding the average rate of change between those two values, they're getting closer and closer. Same thing in this direction. We're getting closer and closer to 3, just a little above. Now our difference quotient notation over here, this is just how we could rewrite it. So if I'm looking from 3 to 2, that would be the same thing as looking from 3 to 3 minus, 3 minus 1 instead of writing it as 2. So we're seeing an h of -1, h of -0.5, so on and so forth. So what we're going to do is use our simplified forms just for simplicity here, where this found our average rate of change for our function, and then for our difference quotient, we had -4t minus 2h. And what I want to do here is show you that for these scenarios of making tables of values, we could start plugging in here, no problem. But I want to show you a trick with Desmos and how it can create tables for you for simplicity. So first thing we would need to do is to define our function. And something I'm going to do is, since T0 is staying the same, I'm just going to call it 3 instead of T0. Because really with our tables, we can just have a single input. So what we'll do here is I'm going to define a function f of x where we take -2 times 3 plus x. And then what we're going to do is this little plus symbol lets you add a table. And then what I'm going to have is a table of values. And for x, I'm going to plug in all of these T1 values. So I'm going to have 2, 2.5, 2.75, 2.9, 2.99, 3.01, 3.1, 3.25, 3.5, and 4. And what I'm going to do is where I have y1 up here, I'm going to rewrite that as f of x1. And then it's going to fill in everything for me very nicely. So what we're going to see here is we start at -10, then it goes to -11, -11.5. What you can see here is we're getting closer and closer to -12. And we jump to a little below -12. And then we get further and further away. So what I'm just going to write here is that as we get closer and closer here and here, what we're approaching is -12. Let's see what happens with the difference quotient. So what I'm going to do is change my function, and instead of t, I'm just going to put 3 there. So it's really going to be -4 times 3, so -12 minus 2 times x. And I need to change my table so that it matches those values. Let me just adjust my screen here so I can see everything. So I'm going to have -1, -0.5, -0.25, -0.1, -0.01, and then jumping above to 0.01, 0.1, 0.25, 0.5, 1. Okay, so in this table right here, what I'm seeing, we're starting at -10, and we're getting closer and closer to -12, and then we jump to a little below -12, just like the other table. These tables are exactly the same, and it's because we are calculating the same thing, just with different forms. So what the table is doing by analyzing this average rate of change or this difference quotient with these smaller and smaller intervals, what we're doing is getting a glimpse at what kind of change is happening at exactly 3. So t equals 3, that's going to be our October, I think is what we set up above. Yeah, so on October 1st, the bee population was decreasing by 12,000 bees per month. So what we can get an idea of is how is the population changing at that exact moment in time, just then, as opposed to where we started, which was looking between 2 months. Now we could look exactly at one point in time. And that's where we're headed with calculus. And we're going to start with a lot of these formulas with average rate of change and that difference quotient, but then we'll move into some actual rules for how to calculate that given any sort of function.